applications engineer with Trimec Solutions out of the Pittsburgh, Pennsylvania Trimec office. I started using CAD tools in the 1980s, and after 20 years of real-world drafting, design, engineering, and project management experience, I started working with Trimec Solutions in 2006. They brought me on board. I'm coming to you today live with a video tech tip in celebration of SOLIDWORKS 2021, the most recent release, the 15th release of SOLIDWORKS that I've worked with. These live video tech tips are typically sent out to our subscribers via email, but again, in celebration of the release of 2021, we're bringing them to you live during our month of Tech Talks. Here during the month of October, we have over 40 different tech talks in a variety of topics. I hope you've signed up for some, and if you haven't yet, please go to www.trimec.com, and right on the landing page, you'll see a link there for our tech talks. We'll appreciate it. So the topic for today is troubleshooting and repairing imported models. Using geometry from vendors and clients and online resources is an important part of design for many SOLIDWORKS users, but the quality of our neutral CAD data or CAD-native data can vary widely, and it's important to validate and fix any issues that you may encounter before they become problems. Well, what can go wrong, do you ask? Well, you may end up with bad parts that you can't add new features to. I'm sure we've all encountered that at some point or another. Another typical symptom is you end up with these wonky drawing views that won't take on the high quality appearance. Or you may end up with detail views where lines seemingly disappear. Another symptom of a part or a component with bad geometry in the import is when you get poor assembly performance. Suddenly you're cruising along and then you bring in an imported part and your performance really goes through the floor. So these are all the kinds of things that you would want to consider when you're bringing in imported geometry. Oh yeah, and let's not forget finite element analysis. Less than precise imported parts can wreak havoc with an FEA mesh. So today, what we're going to do is we're going to cover some of SOLIDWORKS methods for importing geometry. We'll take a look at some tools that we have for evaluating and repairing bad geometry in imported parts. And we'll take a look at some tips for identifying typical problems. So let's get into it. So quickly put here, SOLIDWORKS has two methods to bring in non-native CAD data. We have a classic translation method that's always been on the file open dialog, where we simply from file open, we can bring in neutral files such as IGES or STEP, or native CAD files from other CAD systems like Inventor, Creo, and Solid Edge. There are a variety of settings as to how SOLIDWORKS brings in those files available under your system options on the import section. And there's no reference back to the original file. In other words, when you bring this in using a classic translation, there's no link back to the original native or neutral file. Now, back in 2017, SOLIDWORKS introduced 3D Interconnect, which is a new technique for bringing geometry from other CAD tools into SOLIDWORKS. The folks at SOLIDWORKS Corporation don't want us to even use the word translate. They want us to call it a direct read. But the takeaway for everyone is that it's actually a different set of algorithms than the classic translation. You can bring in all the same file types as you can with the classic translation, including CATIA models in the professional bundle, the premium bundle of SOLIDWORKS. But the difference is that it maintains a live link back to the third-party file, kind of like what we expect when we're working with native SOLIDWORKS files. And if you make a change or replace the neutral file or the native CAD file from a different CAD system, any downstream documents that use that geometry will update automatically the same type of response that we expect from native SOLIDWORKS files. We now have that ability with importing 3D CAD data. But again, the takeaway for you folks who aren't interested in maintaining the link is that we have essentially two algorithms for bringing imported data into SOLIDWORKS. And if one doesn't work to your satisfaction, it's pretty obvious you should try the other technique. And we'll take a look at that as well. Regardless of the technique you use to bring geometry into SOLIDWORKS, we have a handful of tools that will allow us to evaluate the quality of that geometry. And we're going to run through those as well through the Check Entity tool, the Geometry Analysis tool. Most folks are familiar with Import Diagnostics because that pops up automatically based on your system settings. And then finally, we'll take a look at how we can apply a display style using curvature display to kind of suss out where we have problem entities in an imported model, or any model for that matter. So let's get into the software. So here in SOLIDWORKS, I want you to notice I'm just going to go to File, Open. And here I have a couple of step files that we're going to use as the object of our attention here today. I want you to notice that these step files are identical. Let me slide this over. These step files are identical in terms of their time date stamp, as well as the size on disk. So it's a good deductive trial to see how the import is different. I'm going to bring the first one in using 3D Interconnect. By the way, here's a little tip for you. Notice that my file type or my association with the step file is set to Notepad. If you ever open up a step file, I want you to notice that in the header of a properly formatted step file, you'll find in the header information about where that file came from, what was the originating CAD tool that generated that step file. This can be very helpful if you're trying to troubleshoot a thorny import. Maybe you could go back to the source and say, hey, you know, you're running Pro E, I'm running Pro E, can you send me the native file? And now you know. It's just a little tidbit there for you. But what I want to point your attention to is when we bring in the step file via 3D Interconnect, again, the naming convention really has nothing to do with it. What really is important is when we go to our system options under our import section, here we can specify whether or not we want to use the 3D Interconnect technology. And for this first go around, we are going to use that. And I'm just going to open up the file, and it does a direct read. Because of my system settings, I'll get prompted to specify a template. And then SOLIDWORKS brings the file in. Looks great, doesn't it? I want you to notice, if we go back to our feature manager tree, notice that we have a solid body. The 3D Interconnect has done a great job of bringing that in. But I want to draw your attention to the node in the tree that represents the import. I want you to notice that we do not see the typical imported solid node. We have a special icon here of a part file with a leftward facing green arrow that tells us that there's a live link between the geometry we see here on the screen and the step file that was used for the direct read. In fact, if I do a right click on this node in the tree and we go to external references, you can see a typical external references dialog box that tells you the name of the file on disk and where it's located and what its type is. If I were to try to run import diagnostics right now, notice that we get this message that this body cannot be modified and the owning feature must be unlinked to enable the healing operations. So this is a testament to the fact that we brought in this geometry and it still is maintaining a link through 3D Interconnect. Now, as a point of contrast, I'm going to go back to my file open, and this time I'm going to bring in a copy of that step file, but I'll go into my options here and I'll tell SOLIDWORKS not to enable the 3D Interconnect algorithms. And when I open this guy up, it's going to open up in a manner that we're accustomed to seeing, again, from decades of running SOLIDWORKS. The software does its thing, and it brings in our imported file. And I'll change the display style slightly and roll this guy around. And there we get to see again, in this case, a typical imported body. So we have two techniques for bringing in the geometry. In a minute here, I'll show you how we can break the link with the 3D Interconnect import and illustrate how we have actually different outputs, different results, different algorithms that can affect the geometry. The three tools that we're going to use to evaluate the quality of this imported geometry are right here on our Evaluate toolbar. And that's the check tool, the geometry analysis, and finally the import diagnostics. When we run the check tool, we're going to ask SOLIDWORKS to do a stringent check on all of the solid and surface bodies in here and to report back to me any short edges that it encounters, any faces or edges that it considers invalid. And I would prefer to get all of this information back to me. What's the minimum radius of curvature in here? What kind of gaps are we encountering, etc. The software does its thing, and we get a report. And it shows us that the location of, for example, the minimum radius of curvature across this entire model is 0.05 millimeters. But what I think is really cool is you'll notice in the graphics area, it gives us this yellow arrow that points to the precise location where that particular flaw or characteristic is located. I asked this routine to look for short edges shorter than 1 millimeter, and we have a handful of them up here in the boss area at the top of our horseshoe. But what really is causing me some concern are these faces that are being reported back to us as invalid faces. And furthermore, it even shows us in this report field, what is the nature of that invalid face? It's a self-intersecting face. I have a couple other invalid faces here as well, and it reports back to me there's a gap of 0.07 millimeters or so in this neighborhood. So I'm going to keep an eye in this neighborhood because I think this is where we're going to have some problems with this imported file. But now we know by using this entity check that there are regions in here that we have to pay a little closer attention to. The closer attention we can pay to this might be running the second tool in this stack, the geometry analysis tool. When we run the geometry analysis tool, again, it reports back to us similar information to what we saw in the check geometry tool. It'll find small edges or small faces, never Ronnie Wood, any sliver faces that have large aspect ratios, and any knife edges, etc. These are the items here that might wreak havoc with an FEA mesh. The execution here, we have to click on the calculate button, and the software does its thing. And as it runs through all of the geometry based on the criteria, it has found a number of edges that are smaller than 1 millimeter. Again, we're not surprised. It's in the neighborhood of this boss. But what is really interesting to me are these sliver faces that the software has identified. As I click around in the graphics area, you'll notice that instead of a yellow arrow, I get these callouts that point to the neighborhood where that particular geometry is. Again, is this good geometry? Is it bad geometry? Am I indifferent to it? I guess it depends what I intend to do with this particular model. These knife vertices, which are very sharp regions where, for example, the angle peters out to a 0.04 degrees, I know for sure that this neighborhood is going to cause me some heartburn if I were to try to create an FEA mesh. So I might have to go through some simplification activities there as well. Again, so the second tool we have is this geometry analysis tool that allows us to interrogate our model and report back to us meaningful information about the quality of the imported geometry. The third tool in this stack on our evaluate toolbar is this import diagnostics. It does a lot of the same things that the geometry check and the geometry analysis tool does, but in addition, it checks for superposition. It checks to see if any of the faces or surfaces that are references for the faces are overlapping one another, and it'll report that kind of information back to us as well. When I go into my import diagnostics, I love seeing a yellow message at the top of the property manager in SOLIDWORKS. If you ever see a yellow message, read it, because the software is telling you exactly what to do to try to meet with success. Number one, click attempt to heal all. Number two, if any faults remain, hover your cursor over the item and then try to repair it manually. I want you to notice as I click on these various nodes in the problem field, with a right click, I can zoom in to the neighborhood, and sure enough, it's that three-sided patch that's causing me some heartburn. And again, as I hover my cursor over these various nodes, it gives me some feedback with a tooltip. There's a general geometry problem on that face there. I guess it's higher ranking than kernel geometry problem. In any event, I'm going to follow the instructions, and I'm going to ask SOLIDWORKS to heal all of those faces. After a short while, the software does its thing. It reports back to me that it's successfully healed a face, but it still tells us that we have a problem in this neighborhood. I can try a right click to repair that face, and it simply hasn't been repaired. So I got to kind of leave this model in a state where this particular face has a general geometry problem. We'll return back to that in a minute or two. I wanted to go back to the model brought in through 3D Interconnect to kind of show you what that workflow might look like. Back here in the original model that I brought in via 3D Interconnect, I want you to notice that we can break the link between the step file on disk and its representation here in the SOLIDWORKS model. With a right click in the property manager, I can dissolve this interconnect feature. The software does its thing. I will warn you that once you break that link, you can never unbreak it. Once you break the relationship between the neutral or third-party native file, you can never reestablish that. It's only established when you bring it in via 3D Interconnect. But what I want you to notice now is that for all intents and purposes, we simply have a file with imported geometry. There's no evidence here that it was brought in using the algorithms that were part of 3D Interconnect. At this point, I would run through the stack of tools again on my Evaluate toolbar and have it check for any geometry that might cause me any problems or heartburn. You notice that it found, in my case here, the same face with that minimum radius. So that's consistent here, but it did find a set of different edges that are still in that same neighborhood, but the results are slightly different. And that's, again, a testament to the fact that it's using a different import algorithm. Running through geometry analysis again, and we'll run the calculation. Again, this is on the part brought in through 3D Interconnect. And the software does its thing using the same criteria. And it has found a number of problems or issues based on our criteria. And I want you to recollect that the number of short edges and sliver faces is different in this model than it was in the original classic import. And then finally, when we run import diagnostics, notice that in the original model using the classic import, we had 3 faulty faces. In our case here, we have 9 faulty faces. We can click on any one of these guys and try to repair the face or zoom to it. But again, reading the instructions, we're going to just click on Attempt to Heal All, and the software does its thing. And we get a nice green message. I love getting green messages in SOLIDWORKS. And notice that every one of those nodes now has a green check mark. So the import diagnostics was actually more successful on the model brought in through 3D Interconnect, and then with the link broken. One final thing I want to show you is the ability to evaluate the geometry or the topology of your model using a tool, again, on our Evaluate toolbar called the Curvature Tool. What this does is it changes the appearance of the faces of a model and applies a color coding that reflects the curvature, or rather the radius of curvature, at a certain locations, at any given location on the model. So if I go back to my original base frame that was brought in using the classic translation, and I turn on the display of our curvature, I want you to notice that suddenly the model starts getting color-coded faces. As I move my cursor around, notice we're getting feedback, and it's telling me what the local radius is and the radius of curvature at the precise location where the tip of my cursor is. If I hover my cursor over a planar face, you'll get feedback that tells you that your curvature is 0. But what I want to draw your attention to is how the geometry is a little convoluted in the neighborhood of this boss. You got to pay attention to the values. Even though the values are changing, the magnitude of the change is insignificant in this neighborhood. But the real proof in the pudding, remember this neighborhood where we had a problem with this 3-sided patch? When we turn on the curvature display, it's obvious now that there's some sort of issue with this 3-sided patch where the curvature changed dramatically in this little divot location. Is this good? Is this bad? Is this just ugly? Well, that's for you to determine based on what you intend to use the model for. But again, if I was going to run analysis or attempt to pull toolpaths off of this, I'd probably want this geometry to be cleaned up a little better. As a point of contrast, when I flip over to the other model that I brought in via 3D Interconnect, and I turn on the curvature display, I want you to notice that the profile of this 3-sided patch is consistent, and we don't see that little divot like we did before. So we've basically been able to illustrate where we have a defect in the topology of our model, as well as the contrast that is evident because of the way we brought the imported model in. Let me show both of these. And there you have it. The left model, the import was brought in through 3D Interconnect, and the right model was brought in through the classic translation. So there you have it, folks. I hope this has been helpful for you. Please post your questions in the comments, and I'll be sure to answer them. Our next live tech tip is going to be on Friday the 9th, again at 11 o'clock, where the topic about using Windows Clipboard in SOLIDWORKS will be brought up. I think it's a great topic where you can leverage a skill set that you already have to work even smarter with SOLIDWORKS. I also want to remind you to sign up for some of our remaining 35 tech talks that we're presenting throughout the month of October. If you go to www.solidworks.trimec.com, and right on the landing page, you'll find the link for our tech talks. If you like this session, you may want to sign up for our Throwback Thursday sessions, where we revisit some best practices and explore new functionality in SOLIDWORKS part modeling, assembly modeling, sketching, etc. Thank you all for attending today, and I hope these tips have been helpful, and I look forward to coming back to you soon with some more tips. Have a good day.